So now welcome. So this is the first of what will certainly be many webinars hosted by the Collaborative for Research and Origins, CREO, which is an online institute where we share knowledge about space and life and the history of our planet in the context of the universe. And today, the topic is Pangea and you. Well, why don't we begin by just talking about what Pangea is? I mean, what does it mean? Have you ever heard of it before? Who came up with this idea? How do we know that Pangea existed? Well, Pangea means all lands or across all land. Pan, across, like panorama, panoramic, pan-national. The other is Gaia or Gaia, which means land or earth. So Pangea means that the lands are together across all lands. The idea is not a new one. Long ago, and I'm going to share my screen now, here. I hope you can see that. Bring this over. Let me know if you can see that by giving me a thumbs up. Okay, so you should see a map of the Earth, but it's a really weird looking Earth, right? You can see some of the outlines of familiar land masses here. Here's Africa, for instance, the largest, oldest continent on the Earth. Here's Antarctica. Here's Australia and India, sandwiched between Africa and Australia. And South America and North America here. Immediately, I think you can see that this is just the kind of puzzle piece that you would expect given the shapes of the continents, right? I mean, every kid looking at a globe of the Earth notices that, if you can see my cursor here, notices that, oh, what do you know? South America here fits in like a puzzle piece into Western Africa. North America here also fits in like a puzzle piece. But what is less obvious, and only possible thanks to plate tectonic reconstruction, which tells us where the land masses were at different points in Earth history, can you see that India here fits right next to Madagascar and Eastern Africa, and that Antarctica here at the bottom now kind of fills that hole between Australia, Africa, and South America. Now, this is remarkable, because how can this be? You walk along the surface of the Earth nowadays, it's not like the land is cruising around and like crashing into other bits of land. No, it's entirely possible, if we understand, of course, that the movements of the land masses occur very, very, very slowly. And as we learn in our course, these movements have about the rate of change of the growth of your fingernail. And if you waited millions of years, you would have an enormously long fingernail that would span ocean basins. So just keep that in mind. Pangea. Pangea is an idea that was probably first promoted in the early 16th century by a group of map makers living in Portugal. That's because Portuguese map makers had charted the coastlines of Western Africa here, as well as northeastern South America. And they noticed that the two appeared to fit together. They didn't understand why. And not much more was done about that until the early part of the 20th century, when people started asking questions. Prior to that, most of the time it was just passed off as coincidence. Now, here's something we should all keep in mind. If someone just explains something away to you as coincidence, I want you to think twice, because maybe there's an explanation there, and that coincidence is just a simple way of saying, don't bother thinking about it. Because a famous meteorologist, not a geologist, mind you, a meteorologist by the name of Alfred Wegener, sought to explain this puzzle piece fitting of the continents. And he wrote a book about it called Continental Drift. And in the book, Wegener provided evidence that the continents were once together like this, in this Pangea form. And the lines of evidence that he showed were really good. So one of them was that if you follow mountain ranges, if you can see my cursor here, do you see it? Mountain ranges like the Appalachians here in eastern North America, they run up and they appear to even cross the ocean, and they turn up again in the northern British Isles and Scandinavia. I mean, between the Appalachian Mountains and the British Isles is the ocean basin of the Atlantic. And there isn't a mountain chain that just goes under the ocean and then reappears again. In Britain, no, it's oceanic crust. So it must be, as Wegener argued, that the land masses were together. Other lines of evidence include similar sediments and similar rock types on either side here of North America and Africa and South America and Africa. For example, if you've ever visited Boston and the eastern margin of New England, the rocks there are related to the rocks found in Morocco, not to rocks found to the west, like in Ohio or Pennsylvania. So that is called the Avalonian terrain, and that terrain is a group of bits and pieces and slices of the crust that were jammed against the North American continent when Africa and North America were together. Well, Wegener's idea was met with a lot of opposition. American and Scandinavian geologists said that none of this could be right. There wasn't a mechanism. And so without a mechanism, how could Wegener prove his theory? But that did not prevent him from trying. It didn't help that Wegener was not a geologist. He was a meteorologist. So geologists were saying things like, well, how can a meteorologist tell geologists what is going on with rocks? But Wegener persisted, and he even set up experiments where he tried to measure the rate at which the continents were drifting with respect to one another, using the positions of stars at different times of the year. The problem there is that the rate of drift is, as I mentioned, so small in an individual year that it would take many decades using Wegener's technique in order to resolve differences in the position of the plates. After Wegener died, his idea did not die with him. Other geologists, and principally a geologist from South Africa by the name of Alexander de Toit, thought that Wegener must be right. I mean, the evidence kept accumulating. And so de Toit followed this evidence, and he presented several more lines of reasoning to bolster the continental drift theory, which is what it was called in those days. And one of them was that de Toit showed that there were fossils of a reptile on either side here of South America and Africa, and they were the same fossil reptile, right? They're found on opposite sides of the Atlantic now, but this fossil reptile is a small reptile, and it lived in fresh water. So a habitat that is unattested in the Atlantic Ocean. So de Toit proposed that these fossils came from one locality, which, when the continents separated, was split, and the geological record of that single locality was divided by the two continents. Another line of evidence is from glacial markings called striae. So de Toit found that he could link up the directions of marks made by glaciers running over the surface of the Earth at different times in Earth history that all lined up between South America, Africa, Madagascar, and so forth. Well, despite this growing evidence, geologists remained unconvinced. Then something interesting happened. There was a development of submarine navigation. And you might be wondering, what does submarine navigation have to do with Pangea and continental drift? Well, imagine you're in a submarine underwater for days or weeks at a time, and you cannot surface. How do you know where you are? And you say, oh, well, just use a compass. Well, a compass is going to just indicate to you where north is, or south, or east, or west. It's not going to tell you the latitude, right? It gives you, it just tells you the direction of north. Now, besides latitude and longitude, you also have to map the sea floor. You have to know if you're in a submarine that you're not going to hit an underwater or undersea mountain. So what the navies of the world did, and I'm going to focus on the United States Navy, is that they mapped the seafloor, number one. And number two, they found that they could use the magnetic properties of rocks on the seafloor to figure out where they were. They didn't understand why, mind you, that the rocks had these properties, but they just mapped them out and said, okay, this is top secret, but this allows us to find out where we are. So that occurred in the 1940s. And that was, like I mentioned, top secret, because what submarines had to do to find out where they were before mapping out the magnetic properties of the seafloor is that they had to surface, right? And then people had to go outside and look at the sun and also look at the stars and figure out what their latitudes and longitudes were. And that was very dangerous if you're a submarine. So with this knowledge, the United States Navy had an advantage in submarine warfare. And it wasn't until the 1960s, the early 1960s, that geologists started using magnetometers to map magnetic features on the seafloor. And the rumor is that people who had mustered out of the Navy and gone into oceanographic research knew about this, and they shared this knowledge with scientists who had to go out and then repeat all of the measurements, because those measurements collected by the military remain secret. In 1961, the first magnetometer measurements of the seafloor were published. And it became immediately obvious that there was a pattern in the magnetic features of seafloor crust. Basically, the seafloor showed a stripe of north direction polarized magnetic field, followed by another stripe of south direction, followed by another stripe of north direction, and another stripe of south direction, and so forth. That is cool. But what was even more amazing is that at the mid-ocean ridges, where there's like a ridge, like of a mountain range that people, including my PhD advisor, Gustav Arrhenius, pointed out were actually volcanoes at the bottom of the ocean. That on either side of this volcanic ridge system, that the pattern of stripes was mirrored. So you would see pattern like this, switch, 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 switch. Geologists saw this and said, well, it must be that new crust is being formed at these ridge axes, and that the new crust is recording changes in Earth's magnetic field strength. When the new crust forms and cools, it acts like a magnetic recorder. And so sometimes when the Earth's magnetic field is switched from north to south, it's like this, right? And other times when the magnetic field switches from south to north, it's like that. So that would explain why there's this repeating mirror image pattern. That's called the plate tectonics revolution. And the 1960s transformed our view of the organization of the continents and their origin and behavior. With that basis of knowledge, we can go back and reverse the direction of this spreading by taking away the crust with these stripes. And lo and behold, we get Pangea precisely as Wegener and du Toit had predicted. There's a famous case where a geologist, a Canadian geologist by the name of Tuzo Wilson, who was a great opponent of plate tectonics theory, looked at all of the evidence and concluded that he must be wrong and that plate tectonics must be right. And Tuzo Wilson went up and gave a speech where he laid out plate tectonics theory. And J. Tuzo Wilson and others who were there with him, including Kevin Burke, who was a personal friend of mine, and their students like Peter Molnar and others, participated in the plate tectonic revolution. And that has forever changed our view of the nature and history of land masses on our planet. And it's also something that it's very, very humbling, because actually this revolution in our understanding didn't happen long ago. It was actually relatively recently. It was in 1973, I think, that the geological community finally said, yes, this must be it. And Harry Green, a professor at University of California, Riverside, who I also know very well, he likewise showed experimentally and using high temperature melting experiments how you get rid of ocean crust at subduction zones, like at the edges of the plates where they get recycled as a counterpart to the production of new crust. So what does this mean for you? Because the topic of our webinar today was plate tectonics and Pangea and you. And that is, think about where terrestrial life lives. I mean, to be terrestrial, you live on land. And the lands are obviously moving. They're doing this gradually, but they're doing it on long enough time scales so that gradual change in the environment builds up as a progressive selective pressure for biological evolutionary change. This is what's really important. A continent that spends a long time at the equator, as it gradually drifts to higher and higher latitudes, it's going to experience less and less solar insolation, colder and colder climate, which will select for organisms at a fundamental level in their ability to adapt to those changing climates. The interesting thing about Pangea and what it means for you is that climate in Pangea time remained relatively stable. Occasionally, one part of Pangea would slip to a polar region, mostly in the South Pole. Ice would build up there, ocean levels would drop, but then plate tectonics would continue and Pangea would move away. The ice would melt, sea levels would rise. So you have this exposure of land and then flooding of land, and the forests that resided in these coastal areas would become flooded, covered with sediment. And by the way, this leads to our great coal deposits. So Pangea is something that it was an event in the plate tectonic history of the Earth at a pivotal time, just before the appearance of dinosaurs and of mammals. And when Pangea broke up at the end of the Permian, the beginning of the Triassic, it resulted in extreme burial of organic matter and a plunge in carbon dioxide levels of the atmosphere and cooling of the planet. In fact, the biogeochemical cycles were completely out of whack. They had been stable for a very, very long time. But then Pangea itself, as a continental assembly, was no longer stable and began to break apart. Changed the global environment forever, but the echoes of that, biologically speaking, continue today in the proliferation of conifer forests in areas like in cold climates and in dry climates. That lizards and snakes and other reptiles prefer warm interior continental type climates, Pangea type climates. the coal deposits of the world, a lot of them were deposited in Pangea time because of these vast forests that covered the planet. It's remarkable how much of an effect something that existed 300 million years ago still has on life on our planet. So that's what I wanted to share today. Some thoughts about Pangea and you and me. And if you have any questions about any of the things that I talked about today in this webinar, reach out to us at creo.space. And keep an eye out, again, for future webinars as they're announced. And all of these are being recorded and shared on our website for free distribution. Join Creo. It's an exciting, interesting community where we share what we know because it's cool to be smart.